Hello, and welcome to the fifth lecture in the series on scanning probe microscopy methods for probing ionic and electronic transport. So in this lecture, we are going to talk about the implementation of Kelvin probe force microscopy and related techniques in liquid environment. So the first question you can ask is, why would we want to do the Kelvin probe force microscopy in liquid at all? And the answer is very straightforward. So we know that ambient and ultra-high vacuum, KPFM, is extremely useful in understanding the surface chemistry, the charge transport, the photovoltaic and light-induced phenomena, ferroelectric phenomena, and so on and so forth. It turns out that these phenomena are also of tremendous interest if they occur in liquid environments. So examples being corrosion, electrochemical reactions, batteries, biological processes, and local electrochemistry, and so on and so forth. Therefore, we are really interested in being able to use scanning probe microscopy to understand phenomena such as the structure of the double layers on the solid surfaces, understand the local electronic properties, understand phenomena such as the ion diffusion and charge dynamics at the solid-liquid interfaces and liquids, and understand electrochemical reactions in liquids and the solid-liquid interfaces as well. So the question is, how are we going to do that? So can we take the classical Kelvin probe force microscopy and apply it in the liquid environment? Let's look at a very quick recap of how the KPFM works. So in this case, we have our scanning probe tip. We apply the periodic bias to this probe, and the application of this bias results in the capacitive force, which is proportional to the square of the potential difference between the tip and the surface. If we expand this force into the series, we get that there is a DC component, which is time independent. We have the AC component, which is modulated at the frequency of the excitation voltage. And we have a second harmonic component, which is proportional to the square of the excitation voltage, but does not depend on the contact potential difference of the surface. And using these very simple equations, we can either probe the classical surface potential, as in KPFM, by using the feedback circuit to nullify the first harmonic term, or we can introduce the alternative versions of the KPFM if we calibrate the transfer function or play with the more complex excitation methods. However, the versions of the KPFM we talked about now were implicitly based on the assumption that the electrostatic forces are constant in time. We also implicitly rely on the assumption that the electrostatic interactions are linear with the applied DC bias. And we also assume that the measurements did not change the sample. So obviously, if we move our measurements from ambient to liquid environment, these conditions are generally not maintained because liquids, at least the electrochemically active liquids, contain ions that will move in response to the electrical bias. And the relaxation time and dynamics of this ionic motion and electrochemical reactions are both in the time interval relevant to KPFM and also strongly bias dependent. So the question is, what do we know about the operation of the electrically modulated SPM in liquid till this? So about 15 years ago, my colleagues and I have explored the very similar technique called the piezo response force microscopy and adapted it to operation in liquids. So the reasons for that was that PFM is a very useful technique to probe electromechanical coupling in, again, in ferroelectrics and solids and biological systems. You can learn more about PFM and its applications in the lecture series on the PFM, which I already posted on the YouTube. But at that time, we were curious if the PFM can work in liquid, and the assumption was that liquid allows us to control the tip surface interactions precisely. We assume that we can tune the electrostatic forces through the choice of the ion concentrations, and we can operate in the environments which are relevant to biosystems and energy materials. And of course, there was a disadvantages because liquid environments are chemically active. The cantilever dynamics in liquids is different than cantilever dynamics in ambient. We can have stray electrochemical reactions and currents, and we can have a more complex interactions than in ambient. And at that time, we found out that, interestingly enough, we can run the PFM in liquid environment and we can get a very high quality images. So this is example of the PFM amplitude and phase in ambient environment, and this is the PFM amplitude and phase in the liquid environment, and they look almost the same. So why is it exciting and why is it relevant? It was exciting because apparently application of the 10-volt bias to the tip in water at 800 kilohertz did not produce any stray electrochemical processes. In other words, yes, if we apply high bias to the tip, the water will start to electrolyze at voltages of order of 1 to 2 volts. However, if we apply a very high AC bias, then the water does not electrolyze, so there is not enough time for electrochemical process to start. And that was very interesting study, and that suggests that in liquid environments we can actually operate with the high voltages if these voltages are AC. The second application that led us to the idea of using KPFM in liquid was the scanning impedance microscopy. So scanning impedance microscopy is very similar to the KPFM. The only difference is that in KPFM we apply AC bias to the probe and the DC bias across the sample. In the impedance microscopy, the biases are inverted. So the DC bias is applied to the probe and the AC bias is applied across the sample. And in this manner, we measure the change in the amplitude and phase of the AC bias flowing across the sample. And this allows us to map both resistive and the capacitive elements of the equivalent circuit. So you can learn more about this technique in one of the previous lectures. However, what was really important in the impedance microscopy is that allowed us the way to visualize the nanoscale objects with the very high sensitivity resolution. So these are a few examples of visualizing the transport in nanowires when it is continuous nanowire or broken nanowire or the more complex circuit, or even the tip characterization using the nanotube in this case as the probe. So the important thing about the impedance microscopy was that the screening and electrochemical effects are greatly reduced compared to the KPFM. If I apply the DC bias across the sample and start to image it by the KPFM, I will see the uniform contrast. Basically, the whole sample gets charged. I will also start to see the injection of the ions from the nanoscale object onto the oxide surface, and I will see how these charges are diffusing across the material. And this happens because the DC bias can induce electrochemical reactivity and the charge motion even in air. However, in the impedance microscopy, this does not happen because application of the 100 kilohertz plus biases simply does not allow for ion injection and transport on the sample surfaces. So these observations, both the impedance microscopy and the PFM and liquid, suggests that we can try to run similar measurement in the liquid environment. And here is the example of the 3 electrodes, so on the left, and 3 electrodes on the right. We apply the bias to one of those electrodes, and we start to measure the amplitude and phase of the electrostatic forces directly in liquid. So this is, if you will, the implementation of the scanning impedance microscopy in liquid environment. And interestingly enough, it works. So we see the distribution of the amplitude corresponding to the fringing fields in this type of system. And we see the signal in the torsion mode and the diffraction mode. So the signal was relatively weak. So we explored the frequency and the bias dependence on the signal. And we found that if we do these measurements in air on the same structure, we have very clear amplitude, frequency curve for the electrically driven cantilever. If we do the same measurements in liquid, we have a much broader peak, so they're shifted to the lower frequencies. And but basically there is a signal amplification, and there is an opportunity to study this phenomenon in this fashion. Problem was that we couldn't go well below the 100 kilohertz frequency. So if we work at 100 kilohertz, everything is stable. If we start to go below 10 kilohertz, then we start to electrolyze the water, at least for sufficiently high biases. So you can read more about these experiments in these two publications led by Brian Rodriguez. So when it comes to imaging in liquids, we can easily apply AC biases. And as you remember, in the KPFM, we have two components. We need to be able to apply AC bias and DC bias. So question is, can we apply the DC bias to the cantilever in the liquid environment? And the answer is, of course, not. So if we try to do that, then we very easily start to induce electrochemical reactions. So this is a set of photos taken by Liam Collins, who worked on this project. If you apply bias to the tip, then you can easily produce the bubble. So the water will electrolyze and the bubble appears directly under the tip and start to rapidly grow. You can inverse the direction of the electrochemical process and the bubble will collapse. If you kind of overdo the bias amplification, you can see that the cantilever coating basically evaporated and redeposited on the sample surface. So you can see the shadow of the cantilever and chip assembly on the material surface, and when the tip was closer to the surface, the damage is proportionately higher. So the point is that normal KPFM actually is not going to work in the liquid environment because of the electrochemical reactivity. The question is, what can we do? And the answer is that what we can do is to explore theoretically on a very general level what happens in liquids if we apply a bias between the two electrodes. And what we need to do is to understand the dynamic aspect of this phenomena, so not the steady state processes as in classical electrochemistry, but the dynamics. So what are the relevant length scales? We know that if we apply very high frequency biases of order of 100 of kilohertz and megahertz, nothing happens or nothing irreversible happens. If we apply small biases, things start to react and fall apart. So what are the relevant length scales? So let's consider a simple case of the binary electrolyte positioned between the two blocking electrodes. So blocking electrode means that the ions cannot cross the boundary from the solution into the solid. They can only accumulate next to the electrode. At the same time, ions, of course, electrons can cross the boundary if they want to. So this is the schematics of the processes. If we apply a bias, first we have the immediate ordering of the separation of the positive and negative ions across the interface. This process happens really fast. If we wait longer, then with time there would be a macroscopic flow of ions from one electrode to another electrode. So there would be a violation of the macroscopic of the local electroneutrality. It turns out that in the linear theory, the time scales for this process are defined by Debye length of the system and by the geometric size of the system. So the Debye length is the function of the concentration and some elementary constants, so ionic strength, Avogadro constant, and so on. The Debye length defines the Debye time. This is just a square of the Debye length divided by the diffusion coefficient. We also have a second time scale, which is the bulk diffusion time. So the Debye length and Debye time is the amount of time required to form the charged monolayer on the surface, but it is not enough for ions to move from one electrode to another. The bulk diffusion time defines the amount of time required for the ions to get from one electrode to another electrode. And it turns out that there is a third time called the charging time, which is the geometric average of the Debye time and the bulk diffusion time. So if you're interested in more details, there is an excellent review by Professor Bazant at MIT and Physical Review E, which talks about this phenomena and timescales in more detail. Now, of course, the situation can be much more complicated. So in the real materials, there would be steric and exclusion effects. There would be more complex dynamical phenomena. And if you read the more recent papers from Bazan Group, you can learn a lot about it. But in this case, we are not interested in these details. We are just going to estimate the relevant timescale. So assume that we deal with the typical EcFM setup. So we define some tip sample separation. Let's take it of order of the 50 nanometers and kind of comparable to what we think is the tip radius of curvature. And let's decide that we also define a second length scale, which is a cantilever sample separation, which is order of the 15 microns. And as you remember, the non-local cantilever interactions in KPFM is very important. So this gives us an interval of the relevant length scales as far as scanning probe microscopy is concerned. Now we are going to look at two cases. So we are going to look at the clean water, which doesn't contain any ions other than protons and hydroxyls formed due to the self-ionization. And in comparison, we are going to look at the 10 millimolar one-to-one electrolyte. And obviously 10 millimolar is a relatively low concentration. So it turns out that the Debye time in this case would be 23 milliseconds, and in this case it's 9 milliseconds. The bulk diffusion time in this case is about half microsecond, and in this case it's also about half microsecond. For the cantilever, the time scales are even larger, so this goes in the millisecond time scale, and for bulk diffusion time it goes to the fraction of the second. So what does it tell us? It tells us that the ion mobility results in a very broad distribution of relaxation time. So depending on which process we consider, the one driven by the Debye length or by the bulk diffusion, we can have times that vary from the nanoscales, and of course this is too fast for scanning probe microscopy, all the way to microseconds and milliseconds. But this already getting very close to the time scale of the scanning probe microscopy measurement. So our relevant time scale is about several microseconds for the oscillation amplitude of the AC bias, and all the way to seconds to the local. So in other words, if we consider the phenomena that are possible in the cantilever tip surface system, this time, so going from initial moment when nothing happens to the formation of the adsorbed layer to the formation of double layer and full polarization, these phenomena are likely to happen on the time scale which is directly within the time scale of interest for SPM. More importantly, we don't take into account the nonlinear processes and, for example, electrochemical reactions. We can speculate that the reaction will happen on the time scales comparable or slower to the diffusion time scales, but if you apply higher voltages, then your transport mechanism are going to change. So for high voltages, we will have a transition from the diffusion of ionic species to the electromigration of ionic species. So this basically makes the life complicated, and it basically illustrates that there are multiple phenomena are possible on the time scale of the SPM measurement. So since there are so many constants and they have different dependencies on the relevant time scales, what we can do is to make a diagram that shows the classes of the behaviors possible as the function of frequency and the function of the ion concentration. So in this case, we plot two sets of curves. The full curves correspond to the behaviors of interest for the tip scale. So this is about 50 nanometers length scale. And dashed lines correspond to the phenomena of interest on the cantilever scale. So in comparison, this is the frequency range which is of interest for KPFM. So we are being generous, and we say that we're interested in frequencies from hertz all the way to megahertz and slightly higher. So higher than that, we start to have problem with the cantilever dynamics and photodetector and so on and so forth. Now, if we are operating at, we also assume that we operate at relatively high biases, so of order of, say, volts. So here we don't plot the voltage dimension. So if we operate at very low frequencies of order of 10 of seconds, so with a time scale from tens of seconds to time scale of tens of milliseconds, this is the regime of the possible Faradaic reactions. And the reason why we think that this is the regime for possible Faradaic reactions is because this is the time scale for ions to reach from the tip to the surface. This is the regime when our frequency is so high that ions don't even have a time to arrange themselves next to the electrode. So this is the regime in which the liquid environment, in terms of electrical responses, is indistinguishable from the ambient environment. And of course, this is a regime which we're interested in. So this is the regime when the ion concentrations are of interest for bioenergy and electrochemical research. So practically, it means that we do need to somehow study both the time and voltage dynamics of these processes. Let's do one more experiment. So rather than talk in terms of the time constant, let's just do the direct modeling of the bias-induced ion dynamic in electrolytes. So this is the model parameter. We take two electrodes. We assume that they're separated by 50 nanometers. We apply a 30 millivolt bias step. We assume that the liquid is one-to-one electrolyte with the 10 millimolar concentration. We assume that the electrodes are blocking. And we solve the modified Poisson-Nernst-Planck equation, which allows us to model the ionic motion assuming that there is exclusion effect, meaning that ions cannot form infinite concentration. At some point, they form a dense packing. And this is how the ionic concentration and charge distribution and potential distribution look like. So in the initial moment, ions are uniformly distributed in the system. With time, they start to form the double layers on both electrodes. This is how the charge distribution look like. So in this case, we start to diffuse ions from one end of the system to another and form the local charge imbalance. And this is how the potential distribution looks like. So initially, potential is uniformly distributed, so we have a linear potential drop across the system. And with the charge redistribution, we start to see the electrode polarization. So our potential drops at the interfaces, but no longer drops in the central part of the sample. And notice that this dynamics is very similar to the one that we analyzed for the case of the time-resolved KPFM. And the reasons are exactly the same. Time-resolved KPFM is developed to study the surface ionic dynamic. Here, we look at the bulk ionic dynamic, but in both cases, system is quasi-one-dimensional. So what happens if we model the electrostatic forces in this regime? Turns out that we can take this model and calculate the excess osmotic pressure, which gives us the tip surface forces. And one thing that you can notice is that the forces become very complicated. So for example, if we operate in this regime, which is relatively high ion concentrations, you can see that the dependence on the force on the bias is very non-linear. So it is very complicated phenomenon. If we operate in this regime, which is the quasi-static regime, in this case we have a classical parabolical force. So this double oscillation means that we have a first and second harmonic component. So it's great. It tells us the forces and the liquids are nonlinear. So the question is how we're going to measure them. And what it tells us that in this case, we cannot just do KPFM in liquid environment. So KPFM relies on some postulates which are simply not true in liquids, kind of not by a long margin. And KPFM measures only one parameter. So it measures the effective surface potential. In liquids, we deal with the full spectrum of bias and time-dependent phenomena. So perhaps the solution is, rather than trying to measure one parameter, which is useless, try to measure the full voltage and time dependence of the electrostatic interactions. And that's exactly the concept that is implemented in the electrochemical force microscopy, or EcFM. So what we do in the EcFM is that we effectively perform a multidimensional spectroscopy of the electrostatic interactions. And the idea here is the following. We know that for sufficiently high frequencies, the dynamics of the liquid is indistinguishable from the dynamics of the inert atmosphere, which means that we can have a high-frequency AC bias as the basis for detection. So this is really important step, and we do this only because we studied the bias-induced ion dynamics in liquids, and we know that this is true. However, what we are interested in is the time and voltage responses of the ions in liquid. And what we are going to do is that we are going to implement the complex spectroscopy when we interrogate the system by the sequence of the voltage pulses with increased amplitude. We measure the responses after this voltage pulses, and the measurement is based on the sinusoidal waveform, which is quasi-static. So this is our detection principle. This is how it looks like. So this is our excitation waveform. So the measurements are necessarily time-consuming, right? We want to measure the response both in voltage and time domain. We probe the voltage domain by applying the biases of increasing magnitude, and for reasons of reversibility, we make this waveform bipolar, so we go from positive, negative, and so on. And after each probing pulse, we measure the relaxation of the system. And the response over this time interval is measured as the response to the small magnitude AC bias. So we essentially have the three-dimensional probing. This is how the response looks like. So this is our excitation waveform, and this is our response. And all of a sudden, you start to see a very interesting dynamic. So for the small bias pulses, we don't have any response whatsoever. So application of the small bias pulses and then subsequent measurement using this AC waveform doesn't show any changes in our response. But for sufficiently large biases, we start to see that the system starts to be pushed away from the equilibrium state, and we see the rapid relaxation. So if you look at this data, you can see it even better. You can see that the AC response after the bias pulse shows some relaxational dynamic. And if we increase the magnitude of the pulse, then the process becomes much more pronounced. So the way we visualize this data and sort of represent the EcFM dataset is through this two-dimensional diagram. So the way you read it is the time response of the cantilever, meaning the first harmonic of the force for sufficiently high AC bias, plotted as the function of time, so from 0 to 100 milliseconds, and the function of bias, from minus 1.5 to 1.5 volts. As you remember from the previous slide, the measurements is taken from 0 to plus, then to minus, then to plus more, then to minus more, and so on. So what you see here is that for the small biases in the interval from minus 0.5 to 0.5 volts, there is no relaxation after the application of the bias. And for higher biases, we start to see that the system is activated, and we start to see the relaxation process, both for negative and positive voltages. Now, can we look at this in more detail? And since we are doing, in this case, the lock-in detection, we can as well look at the both first and second harmonic of the measured signal, just because we get it for free. And it turns out that we start to see a pretty interesting dynamic, which depends both on the tip and the electrolyte and the electrode. For example, on the graphene HOPG sample, you can see that we don't see any processes from -2 pretty much all the way to 2.5 volts. However, at high negative biases, we start to see the relaxation process, and we start to see some anomalies in the second harmonic signal. In the gold electrode, we start to see that there is no reaction process from -1 to 1 volt. And at the same time, outside of this voltage window, we start to see the onset of the time-dependent relaxation, and the higher the bias, the larger the relaxation time. We also start to see some interesting features in the second harmonic signal. So basically, we refer to this gap when nothing is happening as the Collins gap, which corresponds to the lack of the electrochemical reactivity. And then we have the reaction region. We can further explore how this behavior depends on the ionic strength of the solution, and it turns out that it depends on it quite a lot. So this is an example of the reaction process of the 1 millimolar sodium chloride, 10 millimolar, 100, and 1 molar. And you can see that for the diluted solution, the size of the Collins gap is actually pretty large, and the relaxation processes start only at the high voltages. With the increasing concentration of the sodium chloride, we start to see that the electrochemical reactivity starts with lower biases. We start to see the additional relaxational features, and generally the interval at which the measurements are possible start to narrow down. So the white regions here corresponds to the case where the electrochemical reaction with the bubbling and so on started, and we had to stop the experiment. So it turns out that this EcFM approach allows us to get some considerable insight into the time and voltage dependence of the electrochemical processes. And these are a few more examples of the measurements in the different electrolyte. Now it's potassium sulfate on the gold electrode when the tip is relatively far from the surface. And you can start to see that in the water, so zero concentration of potassium sulfate, we have a relatively open gap, and then for adding the electrolyte, we start to see a very pronounced relaxational behavior. So this basically tells us the interval of the stability of the electrolyte, and it tells us the voltage corresponding to the onset of the Faradaic and electrochemical processes. Question is, can we even call this method the microscopy? What I've shown you is the example of the single point measurements, and as I said, at some point the process start to result in bubbling. Can we do the spatially resolved measurements? And we know that this is possible because the behavior of the EcFM signal depends on whether we are on the gold surface or the silicon surface. So if we have a sample when we have both gold and silicon, we can have different responses here and here. Question is, how can we visualize this behavior? So remember that when we talk about the EcFM, our signal, or if you will, our response and the signal's special pixel is this two-dimensional diagram. So let's start with the simple experiment. Let's repeat the experiment 8 times along the line going from HOPG all the way to gold. And you can see that all the points measured in the HOPG have roughly the same response, so the picture is roughly the same. And all the points related in the gold have similar but different response. For example, look at the long-term relaxation and the large negative bias. It doesn't happen on graphene, but it happens on gold. And look at the width of the Collins gap. So here it is relatively broad, and here it becomes much more narrow. So the question becomes, how can we visualize these measurements? So this is a high-dimensional data because in scanning probe microscopy, we want to do the measurements over the two-dimensional grid. And in this case, our measurement signal is also two-dimensional. So it turns out that the way to do it is to, one way to do it is to look at the cross-sections. For example, we can collect this two-dimensional object at each point of the sample surface over the dense grid. So in this case, this is 10 by 40 points, so it's maybe not that dense, but nonetheless, that's a lot of measurements. And you can see that the spatial localization of the signal, even if we look at the cross-sections as a function of time, shows a very clear boundary between the gold and, in this case, silicon dioxide. More importantly, it shows a number of points where something unusual goes on. So, for example, this particular point It's not a noise. There is something here on the surface that results in markedly different behavior. So looking at the cross-sections of the four-dimensional dataset is one way to do it. But there's another way, which is based on the use of the principal component analysis or other multivariate techniques. So what happens in this case is that we take our four-dimensional dataset and use the principal component analysis similar to the G-mode KPFM in order to separate it in the relevant components. And this is the example of us taking the EcFM dataset on the gold silicon system and separating in the first, second, and third principal component. And these are the spatial maps, and these are the corresponding eigenvalues. And you can see that, for example, this behavior is primarily exhibited on gold, and this behavior is primarily exhibited on the boundary between the gold and silicon electrode. So again, we don't know exactly what this means because the theory for this process is reasonably complicated, but using the purely exploratory data analysis, we can show that we can get the data. It has a very high degree of spatial localization, so we do have the spatial resolution, and we have a behaviors which are specific for individual materials. So at the very least, we have a fingerprints of the relevant electrochemical. So this is another example of the same behavior when we now take the measurements of the two electrodes. So remember the first example of the measuring electrostatic forces in liquids I showed in the beginning of the lecture. So this is very similar local system in the liquid environment. And we can visualize how the first and second harmonic signals are distributed and how they evolve with the function of time and voltage. So this is very exciting field, and undoubtedly it will develop further in the future. And if you want to know more about it, you're welcome to look at the following publications by Liam.